they are the opposite in P. Again, we are relating the two traces in time. So the model checking is desirable, but it has a non-elementary complexity, which essentially depends on the quantified alternation. So if the quantified alternation is zeros, meaning you either have rolls or you have exists, then it's LTL with the usual p-space complete hardness problem. So satisfiability is unfortunately undesirable, but we will not talk much about satisfiability of hyper-LTL. So as we saw, the semantics of the passage of time in hyperproperties is synchronous. What does this mean? It means that the traces are moving in time using the temporal operators in a lockstep manner. However, many systems or many systems we intend to study, for example, software, are asynchronous. We would like to have something like this, where maybe perhaps the first trace goes faster while the second trace stays. And maybe this is because X prime is the execution of a program in a time-sharing system where another component, which is not interesting, is executing. So this passage of time is not really relevant. What we need to know is the equivalent positions in both traces. Hyper-LTL is not good at doing this. So starting in 2021, many different people started investigating asynchronous extensions of hyper-LTL. So for example, in the first paper, what they do is that they introduce a fixed point calculi for hyperproperties that I will present shortly, and the alternating automata variant for the logic. In this paper, in the Leaks paper that I'm pointing out, we introduced two extensions of hyper-LTL, one was called stuttering hyper-LTL, and the other called context hyper-LTL. And this is what we build our work on. And in the third paper that I will briefly present, we introduce something called a hyper-LTL or asynchronous hyper-LTL. So the typical pattern that we follow here is that we take hyper-LTL and we added a feature for asynchrony. And unfortunately, this results in an undesirable decision problem even for model checking. So the typical paper goes along the lines of identifying a desirable fragment of a logic that limits the usage of the logic, but makes a model checking problem desirable. And then there are two important questions. Is this maximal? Can we expand it even further? And the other question is, how do we compare to asynchronous logics? Typically, to have a paper out, you need to find one property that the other competing system cannot express, and you can, or the other way around. So in the Popple 21 paper, the fixed point calculus, essentially what it did is that it added obviously a fixed point temporal operator, a fixed point operator to define the temporal operators, and it had a next which you could specialize for each of the traces separately. So you could ask one trace to progress. So and of course there is the asynchronous variant, but as you can imagine, this logic is undesirable, and the reason for its undesirability is that you can very easily move the traces arbitrarily far apart from each other, having to remember all the steps in between, which requires unbounded memory. But of course, the rigorous argument goes through encoding problems like post-correspondence, for example. In another variant that we introduced, you have the usual temporal operators, and then you have this E or this A, which means that there is a way to align the traces, or for always which you align the traces. So we call these trajectories. So essentially, if there is one trace to align such that the temporal formula holds, then you're happy with this way of introducing trajectories, existential or universal. But now to the point of the paper I am presenting, we introduced in the Leaks paper in 2021 stuttering hyper-LTL and context hyper-LTL. So what do we do in stuttering hyper-LTL? As in hyper-LTL, we have the quantifiers in the prenex form, so the outer quantifiers. And then in the inner, we have the usual Boolean operators, atomic propositions relativized to a single trace, and the two relativized temporal operators for next and until, which are decorated with gammas, and the gammas are essentially sets of LTL formula. So the intended meaning is that the next position is the position in the future of the trace where some of the temporal formulas in gamma change value. So for example, if we have P as an atomic proposition, the next proposition is the next time step is that time step at which P changes valuation. If in the future of the trace there is no valuation change, then it's the next step. So we create an infinite number of relevant positions. So pictorially, so if this is the first position in the trace, which is always relevant, the next position will be that position at which one of the formulas in gamma change value. So if, for example, we have an empty set, then we recover the synchronous semantics. But if we have observation point, interesting point, like, I don't know, an atomic proposition that denotes the interesting observations, then we jump to the next interesting observation. Interestingly, these temporal operators are what is used to compare the traces. So we jump in both traces to the next relevant position that then we compare, and so on. So this is very useful when we can easily identify the interesting time points. And whatever happens in between is not really relevant, or the passage of time is not really relevant. So this logic is undecidable. Again, we can encode many difficult properties, but the evil in our proof was always related to using different gammas within the formula, different sets of LTL traces to denote different ways of comparing the traces. So in that paper, we identified what we call simple hyper LTL S, or simple stuttering hyper LTL, which is a decidable fragment. And the trick goes in the following way. We fix a gamma up front, and then within the formula, every time we are going to use a formula, we can only use the same gamma that we fixed. So we cannot use different ways to determine the passage of time in the traces. And the logic simple hyper LTL S is the union of hyper LTL S for all gamma. But within a formula, you cannot have two different sets of LTL traces to denote the passage of time. The other logic that we introduce in the Leaks paper is what is called context hyper LTL. And the only addition we have to hyper LTL is the following. We add the context operator, which is a subset of the traces that appear in a formula, just to freeze the other traces not in C, and move, when we use the temporal operators within, to move only the traces in C. So if C is always all the variables, this is precisely hyper LTL, so all the traces move at all times. But you can control somehow within subformulas which traces move and which traces stop. All right, so now I'm ready to introduce the main result in the paper, which is a logic generalized hyper LTL. So the main ideas is to combine stuttering and combine context. So hyper LTL S and hyper LTL C, and to allow inner quantification of traces. We will see that in a moment, and also past operators, which I believe is the first hyperlogic with past features. So in a nutshell, the syntax of the logic is as follows. So we don't have the outer quantifiers, so the formula need not be in Prenex form. So, and the quantifier may exist in the middle of a formula, but we have the Boolean operators and atomic propositions. And then we have the quantifier for traces, and we have both context and stuttering decorations with LTL formulas in the temporal operators. So again, these C's here as subsets of the trace variables that appear in the formula. And again, the gamma is the set of LTL formula that need not be fixed in the whole formula. It may change from formula to formula. So again, the passage of time for a given temporal operator is given by the changes in gamma, both back and forth, meaning that we can go to the previous interesting point or the next interesting point in order to have yesterdays as past operators and since as past operators. Okay, so what is the semantics of the logic? So now I cast here the full semantics of the logic. So for atomic propositions, so this pi is essentially an assignment, a map from the trace variables into pointed traces. That means a trace and the pointer in the trace. So in order to evaluate an atomic proposition, we take the trace variable and we take our assignment. So we get the pointed trace that corresponds to X. And then we check the atomic proposition at that precise position of that trace. So we have this way of doing the semantics with this pointed trace, so we can go back and forth with future and past. Now for the existential, this is an interesting point. We spawn a new trace from our trace language, meaning from the traces of the click structure, and we reassign, maybe it wasn't assigned, maybe we're just hiding it, we're capturing it. So the trace variable X is remapped to sigma and position 0. So even if this existential happens within a temporal operator, we remap the variable into position 0, and we don't change the context. So the context is the second component of our semantics. So for the context operator, this is precisely what we do. We change the context to see. You will see examples in a moment. For the passage of time for next, what we do is that we take the next relevant position according to gamma for all traces mapped by pi to all trace variables, and we don't change the context. For the predecessor, for yesterday, we need to check that the predecessor, that for some of them is not undefined, that is that it didn't fall off the trace. And if for all the elements of pi, so for all the traces, it didn't fall off the trace, then we take the predecessor, meaning the previous relevant point. We don't change the context, and we map according to gamma. And as you can imagine, for until and since is the usual until and since definitions. All right. So how does it compare to other logics? So let me compare stuttering or general hyper-LTL to stuttering hyper-LTL. So if hyper-LTL is in prenex form and it doesn't use context, so let me go back for a moment to the definition. So if this is in the outer part, which need not be, but if it is, and it uses no context in the formula, then we get precisely stuttering hyper-LTL. So generalized hyper-LTL subsumes stuttering hyper-LTL. So also, it also subsumes context hyper-LTL. Why? Because if it's in prenex form, which it need to be, but if it is in prenex form, and the gamma is always the empty set, then we're moving synchronously, but we're limiting the movement through the context. So let me go back again. So gamma is always in the formula, the empty set of LTL formula. And the existential is outer in the prenex form, then we get precisely the syntax of and semantics of context hyper-LTL. So we again subsume it. And if we both not use context and gamma is empty, then we get precisely hyper-LTL, our good old synchronous temporal logic for hyperproperties. So again, we subsume hyper-LTL. So an easy theorem, an easy propositions from the previous observations is that model checking the general logic is undesirable because model checking stuttering hyper-LTL and context hyper-LTL are undesirable to begin with. So what do we do then? What we do is identify a desirable fragment of our logic. So if you fix the gamma, as we do in stuttering hyper-LTL, into a fixed finite set of propositions, then we get a logic that is somehow parameterized by this gamma, which we call the simple generalized hyper-LTL, parameterized with gamma, where all the elements in the temporal logic use the same gamma and cannot change. So we fix it. But the other trick that we do in the logic, just for simplicity, is to introduce this pointed quantifier. So the pointed quantifier tells you that there is a sigma I such that the formula holds. So you can go to an arbitrary I that you pick. This is not an addition in expressivity because you can always write it as there exists an X, which is the trace you're quantifying over, such that if you restrict to X the movement, which you can do because you have a context, then eventually when you start moving all the traces again and you follow 5. So this existential allows you to move to a point. The other restriction in the logic, apart from fixing the gammas, which was a trick that made stuttering hyper-LTL desirable, is to have a singleton context. Meaning, if you use a context operator, you cannot use it with more than one trace. You have to restrict your formula to only one trace. So it's a singleton trace that you can use here. And this is an LTL formula, which is only used for X. And then the logic simple generalized hyper LTL is the union of all these formulas that you can use for given gammas. But if you pick two different gammas, then you cannot mix the temporal operators. So one example, let's go to this. There is a trace such that there is a pointed trace Y for which, for all the atomic propositions, it's always the case in gamma. This is the empty here. So this is the synchronous movement. This is the empty decoration. And if we restrict ourselves to Y, this is not the first position in the trace, where the first position is just saying that it's not the case that just said it true. So essentially, we're saying that for every trace, there is another trace, such that in that trace at some point, that is not the initial point, both traces coincide forever. So with this formula, you're saying that for every trace, there is another trace that is a suffix. So example of properties that you can do in this desirable fragment of a generalized hyper LTL is one example is observational determinism. So for example, asynchronous traces with same initial low input are undistinguishable for low users. So in simple generalized hyper LTL, it goes like this. For every two traces that in the initial step, the p variable of X and the p variable of Y for all low input coincide, it must be the case that if you move according to the low observation points, so this is just a set of atomic propositions called the low observations, then for all the p's, they coincide forever. So this may move faster and slower in the different traces. So we're fixing a unique set of LTL formulas, in this case, atomic propositions. Another example, after initialization. So you have an hyper LTL formula, a normal one, synchronous hyper LTL, but the formula must hold in the traces after the initialization phase, which is denoted by an in predicate. So when the in predicate ends, that's when you start evaluating x1 and x2 and x3. And the duration of this prefix of initialization may be different. So the way we do it is that we have this initialization period for x, where we say, if you restrict yourself to x and you take the not in and the first or yesterday in. So this is the first position at which not in holds. So this is what this denotes. And then we have the same Q predicates, and we move with a pointed trace there. And we say, if this is a for all, then we say, if this is a previous initialization point, then implies. And if the quantifier is an exist, then we say, after the initialization phase and the formula, as usual. So another example is global promptness. So this is an interesting hyperproperty where we state that there is a k, but we don't claim which one is the case, maybe 1, 2, 3, or whatever. There is a number k, but that for every trace, every request is followed by a response within k steps. So there is no unbounded response in your set. How do we express it? We say there is a pointed trace x, and this is the interesting trace where we want to claim that this is the longest response. So there is a pointed x such that request holds, and for all other pointed traces y, it could be the same trace for all pointed traces y that have a request, then not p in x until p in y. So since we can instantiate both quantifiers by x, this implies that the p must hold after the q, therefore there is a response after the request in x as well. And the second thing we're saying is that for this x, since not p until py, then we have that this is the slowest. For all the others, we can choose that they're different. P cannot hold before in Y than in X. Therefore, X is the slowest, but X is also a responsive trace. And therefore, the time it takes for X to respond is this K. So this is a non-regular property that we can express in simple generalized hyper-LTL. Another example is diagnosability, where we say that if we see a beta, after the next observation point, all the equivalent traces to the trace I'm observing must have the failure as well. It cannot be the case that we have the same observations, and in one trace we see the failure and the other we don't see the failure. If that happens, then we say that the plan is diagnosable. So what we do is that for all traces we have a beta in X. There is a future observation, so that for all other traces that are equivalent in the observations, in the equivalent observation point, we have seen the beta previously. All right, maybe I have to wrap up. So about expressiveness, we know that generalized hyper-LTL, the undecidable logic, is more expressive than hyper-LTLS because it's subsumed. We have that it's more expressive than simple generalized hyper-LTL. Obviously, one is undecidable and the other is decidable. And it's more expressive than the first order logic of less than an equality predicate. For some simple generalized hyper-LTLS, we know that it's more expressive than simple hyper-LTLS. We know this is the decidable fragment of hyper-LTLS. We know that they're uncomparable. And we know that even this monadic second order logic is uncomparable. The reason for this is that these two logics can only express regular trace properties when interpreted over single traces. So like the suffix property that I explained before. All right. So we also know that the general logic subsumes the epistemic temporal logic and the synchronous and asynchronous semantics with perfect recall. The simple logic subsumes the epistemic LTL under synchronous semantics and the one agent under asynchronous semantics. All right, so for desirability, I will go quickly over this. So the main idea is that we reduce model checking of our simple generalized hyper-LTL. We reduce it to satisfiability of a QPTL formula. And QPTL is desirable, the satisfiability of quantified propositional temporal logic. This is a temporal logic, but where we can quantify over propositions. It's X-space complete, H X-space complete, where H is just the alternations in the formula. All right, so maybe I should wrap up. So in conclusion, we have introduced a new temporal logic for hyperproperties called generalized hyper-LTL, with the intention of being a general logic for asynchronous hyperproperties, fusing the scattering and the context modalities of hyper-LTLS and hyper-LTLC, which makes the logic undesirable. But we have identified a desirable fragment of the logic called simple generalized hyper-LTLS, which is strictly more expressive than our synchronous logic, and all other desirable asynchronous hyperlogics that we're aware of. So the desirability is by an exponential reduction into the non-annotated generalized fragment of a logic, and then through QPTL, which is a type bound. So finally, one open problem is about expressivity, which is whether simple generalized hyper-LTL subsumes, if properly subsumes. We have a reduction in one direction, but not in the other direction. And that's all I wanted to tell you today. Thank you for your attention.
Yeah, so before we go to the questions to the speaker, I think there is this game which Nilzara has instituted, which is we have to ask a question and the audience gets a brownie point. Okay, so here is my question. What is the difference between a property and a hyperproperty? And can you name one hyperproperty and tell me what it is? Yeah, but what is the difference between a property and a hyperproperty? You have to tell me what is the difference between a property and a hyperproperty. Okay, so it's yeah, all right. So So he gets answer. He gets a brownie point. All right, let's go to the question.
Cesar, can you hear me? It was an awesome talk, and I'm very excited to read your paper. I haven't had a chance to read it. Are the pastime operators strictly required? You know, there's this well-known result for LTL that LTL with pastime does not add anything extra in expressivity terms. And if they're not, if you can actually get rid of the pastime operators, what's the complexity transformation?
So the honest answer is that I don't know. I would say that all developments, at least in terms of expressive power, should translate directly into the logic. So for hyper-LTL, this is definitely the case because the constructions go through the usual automata constructions, maybe with a blow up when you have the quantify alternations. For asynchronous logics, I don't want to claim that I'm sure that the translations work because all the algorithms work in a completely different way. So I would say that this is an open problem to know the expressive power and to know whether the complexity, if it's decidable in the algorithms that translate past or eliminate past, would be transferable from trace logics. So the honest answer is that I don't know, and it's an open problem to me.
I have a bit of a follow-up question. I mean, Sisler had this very nice syntactic characterization using pastime operators of safety properties. Does that carry over to hyperproperties? Safety hyperproperties.
This is a good question again, and I must say that hypersafety is a little bit different than safety. Namely, you can play a little bit with the quantifiers and make a formula with only the sense that an extension of your observations that is a failure will always be a failure. So not even using only G. So even if you use only G, you may fall out of safety. So again, syntactic characterizations in the sense of landscapism by Sisla and Soharmana and others are not well studied in hyperlogics, and they may not be difficult, but it's not well studied yet.
Thanks.
Other questions?
Can you say something about more about the decidability of this logic and I mean the complexity of translating it into QPTF?
Yes. So maybe I went fast because I was running out of time. Yes. So essentially, the decidability of the logic goes through a translation into QPTL, but it's not for model checking. So we reduce model checking of our logic into satisfiability of QPTL. So the first is a rather technical proof, but the first few steps essentially eliminate the gamma by encoding the interesting points of the gamma in the cricket structure, for preparation of the translation. And then the translation into the QPTL formula, what we do is that we take, for each quantifier, we take the whole cricket structure and encode it using the quantifier, all the transition relation and everything. And then we put it all together. Of course, it's a little bit technical because you need to add padding for the alignment of the synchronous traces, and we need to also add past operators, which you can have in QPTL. And of course, you end up with a large QPTL formula, and you have to prove, obviously, that the satisfiability of that formula corresponds precisely to a positive outcome of the model checking problem. This is a rather technical proof, yeah, but it's in the paper. So let me see. Also, what we have is a tight bound on this translation, but we have an exponential reduction from our logic into the elimination of the gamma, which we don't know whether it's tight. So this part is tight, but not the first reduction. So I don't know whether that's clear, but all the details are in the paper.
Okay, thanks.
Other questions? Okay, so in that case, I have a small question. E, S1 as E is the equality equal predicate, yeah, level predicate.
Yeah.
But I was wondering why you, when you saw, when you, I slow, in the previous slide, I saw FO with less than and E. That's our tree? The
No, no,
previous.
but in the second order logic, you can define less than in terms of E. This is in the first order logic, you cannot.
No, I'm asking, you
This,
interpret FO
uh,
with less than and E.
yes.
Yes, here. Is it our words or is it over the tree?
Sorry?
The third item, is it over the tree, FO with less than and E?
No, no. This is the equal level predicate between the traces, and this is the comparing the position.
Okay, so less than is only over a branch.
Yes.
Yes, okay. But yeah, so that's my question. Why do you care about FO with less than and E? Because it's ideally you should be taking S2 SE. You should be
No, no.
looking
But
at,
here is the trace logic, right? The second order logic over the one successor, right?
yeah, that I understand.
This
So
is
you
the
are just
equal level
taking,
predicate between
you're
two
just
successors.
taking each over each branch you take the FO or MSO and then you are adding the E predicate. But what happens when you add S2S and E? You take the tree.
Oh,
Yeah.
I see, I see. So
Yeah.
you're asking about hypothetically about S2 SE
Yeah.
as a branching logic.
Yes.
So yeah, I understand. So this S2 SE hypothetically may be useful if you want to compare with hyper CTL, for
Okay.
example. But for hyper LTL, it's sufficient to take the trace successor.
Yeah,
So
but
that's
everything
why
will be
why
inside.
S1S
But everything will
has
be
been
inside
added in
S2SE.
that
Yeah.
context.
Everything will be inside S2SE. All right. Thank you.
You're welcome. Thank you for the wonderful questions.
Let's go to the next speaker. Thank you, Cesar. Yeah, you can stay on, please. You can stay on. This one. Where is pushing? I don't know. Is there any TA in the room? Ah, okay. All right. What's the time now? Ah. All right. So next, yeah, no, I think it will be difficult. You can use that mic. Okay, next we have promptness and fairness in Muller LTL formulas. It's a joint work by Damien Bussato Gaston, Yusuf Al-Hajj, Leo Tibl, and Daniel Varaka. Daniele Varaka. And Damien is giving the talk. Over to you, Damien.
Can you hear me?
What time? He started 11:19. So we will go till 11:50. So you can leave 5 minutes for the questions. Thank you.
Okay, thank you. So, yes, does it work? I can't switch slide. Wait. Okay, now it's good. Okay, so thank you. So today I'll talk about model checking of a particular fragment of LTL formulas and some properties that you might want to add to your formulas in terms of promptness and fairness in particular. So the introduction is based on the general classical setting of model checking, where you have a system that will be encoded as a labeled transition system or typical structure. Here, a server that can stay idle or move to a query state on a ground state. And an execution of your system is an infinite path in this label in this directed graph. Linear temporal logic is defined as usual. So an LTL formula will be able to express properties that you want to see on the path of your system, labels that you want to visit, and in particular, the temporal operators will be used to express what happens in the future. And so the ones that we'll care about here I'm describing them for notation purposes. So we have the finally operator, which is a reachability property. You want to see a label in the future. Globally operator is a safety property. You want to maintain a label all along your execution. And the infinitely often operator that I define here as a shorthand for GF is the Bucky objective that asks that some label is visited infinitely often along your execution. And so I have to reach phi infinitely often along my run. And so you can express properties that talk about what is seen infinitely often, for example, in this way. And so then the model checking problem classically asks if every execution of your system satisfies the property, right? So this is a universal model checking, and I'm expressly using the word universal to distinguish from the pair model checking that will come later. And so in this case, we write that the system satisfies this specification. Now, model checking of LTL is p-space complete. And for our point of view today, p-space is too much, and we'll try to find fragments with lower complexity for model checking. And so, in particular, the fragment that we are looking at is a Mueller fragment. And so Mueller formulas are restricted to only using the infinitely often operator. So instead of having next, until, and so on, you only have the GF as a shorthand. And so you can write Boolean combinations of Bucky objectives in this way. So I want to see B infinitely often, or A infinitely often, and C finitely often, right? And so this is the kind of formulas that you can write in this fragment. And so Mueller formulas can be model checked with a lower complexity than general LTL, and in particular here, CoNP complete. And so from an expressivity point of view, they are quite general for what we do with crypto structures. So you can express Bucky, co-Bucky, state, rabin, parity objective, and so on. However, one limit of that I find to use them in practice would be that the fact that an event can happen infinitely often isn't really telling on whether it happens with a positive frequency or not, right? Like, is it really reoccurring often in practice in the sense that people usually mean when they say this? Is not enforced by a standard Bucky objective. And so for a very simple example, if you have a B that happens and then 2 A's and 3 A's and 4 A's in between your different B's, the frequency of B will be 0. Despite satisfying the Bucky objective. And so we would like to get rid of such runs and consider that they're not really satisfying the infinitely often meaning that we would like to have. And so you can't do that with standard LTL. You could hardcode a fixed frequency, but if you were just asking for a non-zero frequency, you would need some kind of parametric approach. And so that's what promptness proposes. And so prompt LTL, PLTL, adds an extra operator, which is a bounded finally operation. And so FP, so prompt finally, asks that the label that you want to see is seen within the next test set. And so to evaluate an FP formula, you need to be given a run on the bound, right? And you will say that it satisfies it for this particular bound. And so then the model checking problem here will ask for universal bound over every pass. You want to know if there is a global bound K such that every pass satisfies the prompt LTL formula for this bound K. So this would be PLTL. And PLTL comes at no extra cost compared to standard LTL. Here it's still p-space complete to add this FP operator. And so naturally, we've considered we consider the prompt Mueller fragment, where what you're asking is you're only allowed to use the G of FP instead of G of F. And so instead of asking for an event to be seen infinitely often, what you want is to have a bit of a sliding window of length K, and in every window, you want to see an instance of the event that should happen infinitely often. And in this way, if you see an event in every window of length k, you know that you can enforce a positive frequency of 1 over k in this case. And so, as an example, the run that visits A twice and then alternates between B and C will satisfy Fp infinite of B with a window length of 3. Indeed, you need a window length of 3 at the beginning to see your first B, and then a window length of 2 is enough for what happens after that. On the other hand, if the initialization sees too many A's, then you don't satisfy the Fp infinite of B for a window length of 4, for example, here, because you have 4 A's, right? And so this is something, it's like, so yeah, it behaves like a constraint that you want to enforce all along your execution, like globally. And so in this paper, we've looked at the complexity of model checking for this Prompt-Muller fragment. And our main complexity result in terms of our main complexity result is that it's still co-NP complete. So just like PLTL came at no extra cost compared to LTL, Prompt-Muller comes at no extra cost compared to Muller. So this is the main technical result, and then we see what we can derive from this result after. So to give you some intuition of how do we get this model checking result, the intuition is, well, we're going to do a co-NP algorithm. So we'll essentially start from an instance of a system that does not satisfy formula and try to explain how we can guess witness for counter for the fact that this system contains a counterexample run. And so here, how do we do this? Well, there are several difficulties. The first thing that you can see is that the problem asks for the existence of a bound. So if you're looking at a negative instance of the problem, you need to find a counterexample run for every bound, right? You need to show that every bound, for every bound, you can build a run that breaks it. And so in order to have a finite witness, we first explain how to limit the bound. And so the intuition starts very simple. If you have a run on a given bound that doesn't satisfy Fp infinite A, so A is infinitely open in a Prompt manner, what this means is that somewhere along your execution, you have a window that doesn't contain any A, right? And so here, very clearly, this run could also be used as a witness for a smaller k, right? If I cared about a smaller window length, I could just pick a smaller window within this window, and it could also be a counterexample. Now, if I want a bigger k, what I can do is find some loop, assuming the k is big enough to contain a loop, and do a simple pumping argument and conclude that this same path can be used as a witness for any larger window that I would want, as long as I can find a loop to pump. And so what this means is that it's enough to check the bound size of the system +1, because in this way you can pump. So this works very intuitively for this Fp infinite A formula, but in general, if you have a more complex formula with nesting and Boolean combinations, the proof becomes a bit more involved, but this is a general principle. You find something to pump and some ways to pump them, some cycles to pump, some way to pump them in order to break all of the elements of your Boolean formula in a satisfying way. Now that we've said this, we can restrict ourselves to one singular bound k and consider how do we provide a witness for this infinite run that doesn't satisfy the property for this bound. And so let's start with this example here. If my system is A, B, and my formula is I want to see A infinitely often or B infinitely often in a prompt manner, well, if I wasn't prompt, this system would be satisfying, right? Because either I stay in A or I go to B. But because I am prompt, I will be able to build a run that will break both of these subformulas. First, by staying in A long enough to have a window that doesn't contain any B, that will falsify this. And then by staying in B long enough to provide a window that doesn't contain A for a long enough time, right? And so what this shows is that if I want to convince someone that there is a run in this system that doesn't satisfy this property, it's enough to show them these two windows and show them the reachability from the end of the first one to the beginning of the second one, in a way. So this is the intuition for what our polynomial witnesses look like. It's a bunch of windows that are enough to falsify the different parts of the different instances of this infinite operator that are happening in your formula. Now this gives a good intuition, but in general you could have nesting in your formula. And so what does it look like in general? What does the witness look like in general? What we do is we build a structure that explains why this run doesn't satisfy here the formulas that I've given on top, f infinite a and f infinite b or c, by providing the detail of from what point are the subformulas not true. So remember, I'm doing co-NP, so I care about negative instances. So at the start, what I need to show is that the initial position doesn't satisfy the global formula, right? The suffix of row starting from 0 must be falsified on this entire formula. So what does this imply? It means that somewhere, because my formula starts with an FP infinite, it means that I should find a window of length k where this subformula is false at every index, right? And so because this is a conjunction, I have a choice in order to break it on whether to falsify the left-hand side or the right-hand side. And in this example, for example, let's say on the blue segment, it's the the right-hand side that is falsified, and on the red segment, it's the left-hand side. And so here you can check that this portion of the window will be assigned to A, I mean, to this subformula. And indeed, here, A is not true on this segment. And for the other segment, no, for every other position, I have to falsify this disjunction, meaning I have to falsify both subformulas. And so indeed, I don't satisfy C on this blue part. And also, no, I need to show that I don't satisfy f infinite of B from any of these positions. And the intuition here is that in order to break f infinite B on any of these positions, I need to find a window that happens after the greatest position in this set that doesn't contain B's, right? And so this gives some intuition into the kind of things that are happening. So I need to find windows that break some subformulas that I can split between the subsets. And then I need to find other windows when I have nesting that happens after. So the order in which my windows happen is important. This I3 has to be greater than I2 in particular. So it behaves a bit like an until operation. And so with this intuition, I get a witness that I can guess in polynomial time. Here, I only need to guess this labeling of my formula. I don't need to guess the actual infinite path. And then I need to check that from one window to the next, indeed, there is at least one path that links the two of them. So this gives me a nice co-NP algorithm, and then the completeness from I would say, a classical reduction from that. That would essentially encode reachability as a prompt property. Now, the second intuition that I would like to add on top of promptness is fairness. So if we start from our initial motivation, this system that does not satisfy the fact that I can guarantee seeing B infinitely often, here it's clear that the only way in which I don't see B infinitely often is if I remain in A forever. And so this assumes that the choices that are made in my execution are adversarial, right? And so another point of view would be to say, well, what if the non-determinism is not resolved in an adversarial fashion? In particular, what if it's a probability measure? What if what I have is a Markov chain, for example, right? And so in this case, staying in A forever would have probability 0, and I don't need to care about this sign. In this case, I would satisfy the fact that I see B with probability 1. And so what we look at under fairness is we assume that the non-deterministic choice are using a uniform distribution. The actual distribution doesn't matter because we only care about sets with probability 1 or 0. And then the question, the fair model checking problem asks if the set of executions that satisfy your property have probability 1. And so in this case, we say that the system satisfies the specification almost surely, right? And so this system satisfies F infinite B almost surely. So if you look at LTL, you can solve the fair model checking problem in P-space. Oh, we've lost the slide. Back, but not here. Okay. Okay. So for LTL, fairness is still P-space complete. However, if you look at Muller formula, right, so Boolean combinations of Bucky objective, the problem becomes linear now. Because what happens infinitely often in a Markov chain is easy to analyze. You only need to look at the bottom strongly connected component because you will end up in them with probability 1. And then every state in a bottom strongly connected component will be visited infinitely often. And so you can solve linearly for Muller formulas. Now, what if you want to do fair model checking of prompt formula? Well, for general PLTL, it's still P-space complete. And for prompt Muller, what we've shown is that as a corollary of the previous reasoning, a system will satisfy a specification if and only if it satisfies it in a fair way. So the left to right direction is obvious, but the right to left direction means that whenever you have a counterexample, you have actually a full cylinder of counterexample. And this should come as a simple corollary from the witness that I've shown before, because you only cared about what happens within your windows, your counterexample windows, and what happens after the last window. Those shouldn't change the fact that it's a counterexample. And so having one execution that breaks your property means that you have a probability of breaking your property that's strictly greater than 0. And so as a table here, we show that whereas fairness allowed you to get a better complexity for Muller properties, for prompt Muller, the two problems coincide instance-wise. So this is a bit counterintuitive for what we wanted, because my motivation was to talk about things that happen with a positive frequency. And in particular, one observation that you can make is that this system that we said, oh, if the environment is not adversarial, it should satisfy F infinite B. Under promptness, it still doesn't satisfy it, even if you look at almost sure properties, because the probability of staying A long enough to break your window will be non-zero no matter the window length that you pick. However, in this setting, if it's a Markov chain, then almost surely you will see B with a positive frequency, with a frequency of 1/2, in fact, because you will always end up in this cycle. And so what this shows is that the prompt finally operator here is not really capturing what we wanted. And the intuition is that it's because it's not prefix independent. Prompt F infinite operator very much cares about what happens in the beginning, especially if you have a counterexample window in the beginning. And so this is why it's not really capturing the kind of things that you want when you want to talk about something happening with a positive frequency. And so in order to combine both in a nice way, what we propose is a prefix independent variant of prompt Muller, where you force the prefix independent in your formula by adding an F in the beginning, very simply. So it's a very syntactic approach, where you add a finally operator and you say, well, if I see B in every window of a given size after a finite prefix that can be as long as you want, then I can still guarantee a positive frequency for B. So that's good enough for me, and that's what we looked at. And in this case, what we've shown is that indeed you get a polynomial complexity for prompt Muller, assuming prefix independent, because once again you can reduce your analysis to bottom strongly connected components, and then you can show that each bottom strongly connected component is either completely good or completely bad, and intuitively for a given F infinite subformula. So in conclusion, what we've shown is the blue part, that for prompt Muller formulas, the universal and fair model checking are coherently complete, and that in the prefix independent variant, you get something that matches standard Muller formulas that are not prompt, and that are prefix independent, obviously, as Bucky is, where you get coherently on pita. Yeah, we are missing a lower bound, indeed. We are missing a lower bound. All right, and so if I can finish on some perspective on the limitations of this approach. First of all, is that what we've noticed is some counterintuitive behavior when you add promptness to Muller formula, to the GF construction, because essentially F infinite was prefix independent, prompt Muller is not. What we've seen with the order in which the counterexample windows have to happen is that sometimes you can express in prompt Muller properties that look like an until. You want to see an A in every window until a point where you see a B in every window. And this is something that you can express in prompt Muller. And it's not something that you can do at all with a combination of BP objective. And so it might not be an ideal solution, especially because when you express frequency, what we've said is that satisfying an FP infinite property allows you to enforce that B happens with a positive frequency, but the converse is not true. If you look at this example where I see 2A, 2B, 3A, 3Bs, and so on, the frequency of B is 1/2, and yet I don't satisfy FP infinite B because I can always find windows big enough to break what I want. So we would like to, in the future, look at other ways to talk about the frequency of events, and still in a way that links up with LTL tools and LTL notation and reasoning. Thank you for your attention, and I'll take questions now.
Yeah. So my question for the audience: what was this argument for getting the bound on the K? Now I'm not going to make it simple. Last time Sanjeeva I just gave it like that. So he wanted a K. So FP GFK. All right. Yeah, tell me. So how do you know the K? Yeah. All right. Okay, that's it. Thank you. So he gets a brownie point. Okay, now over to questions.
Thank you. Thank you for being talk, Damien. I wonder, when we're speaking about fairness, I mean, this is a struggle that is now very private security. So here, by fairness, you mentioned that you have a kind of, I think, voter. Is it okay?
Yes.
Sorry. Okay. So it's somehow connected to uniform distribution. Would it make sense to consider some other kind of distribution? Because, I mean, okay,
Yes,
the fairness is uniform for certain things, but for instance, for certain things, the normal distribution is more,
Yes.
I mean, a fair distribution.
So thank you for the question. So there are different ways to define fairness indeed. There is the, you can talk, you can consider different definitions, and because we're looking at finite structures, a lot of these definitions match and they are equivalent. In particular here, the reason we use uniform distributions is for simplicity, just to have an easy definition. If you're looking at a Markov chain with arbitrary probabilities that you are assigned to resolve the non-determinism, it doesn't change the set of sets that have probability 1, in fact. And so here it wouldn't change the fact that the two problems coincide, and it wouldn't change the fact that you can reduce the analysis to bottom strongly connected component in the same way in the prefix independent case. The other way to define fairness would be to look at a more topological approach, where you define essentially sets of paths and talk about whether they're meager or not. And so here on finite structure, it's the same. On infinite structure, it would be different, and that would be that it's an interesting thing to look at.
Hi, can you hear me?
Yes.
Okay, so in prompt LTL, all we require is before your formula is satisfied, it's existential.
Yes.
But K could be arbitrarily large. I mean, it's up
Yeah.
to S plus So if you are given like explicit k, does the problem become easier? Does it?
So if instead of having a parametric fp, you have an fk where the k is written, right? Then essentially you can see it, you can, well, if k is in unary, right? It will, it wouldn't change anything from if you don't have this fp at all. If it's in binary, I guess, I think you'd get an exponential blow up. So I would think you'd get some kind of, well, not really pseudo polynomial, but pseudo p space, I guess, answer. Yeah.
Thank you.
So this is a follow-up on the fairness question. There is this model where instead of taking concrete probabilities, you say, well, I have two transitions. Eventually, I will take both, but I'm not going to fix the probabilities. You can think about ordinary probabilities or so. And
Yeah.
since you mentioned that the whole approach is based on the bottom end component, is it on computing the bottom end components, on verifying that they are bottom end components?
So essentially, because we only want we want a p-time algorithm here, and so you can just compute your bottom SCC, right? And so this is something you don't need to guess and check them. You can just compute your maximal bottom strongly connected component. That could happen. I mean, maximal. And then because you know that every state will be seen infinitely often, even with this alternative definition, if you don't want to pick probabilities, this is the probabilities that you care. This is the properties that you care about. In fact, right? The fact that everyone will be eventually seen over and over again. Then you can, for a given BSCCs, completely resolve every f infinite operation. You can either it's true or not. Either this label appears somewhere in the bottom STCs, and in which case BP will be true, or it doesn't appear anywhere, and in which case it's false. And so for Muller formulas, this is a general principle. Now, when you're prompt, you need to add an extra check where it's not enough to know that you will see someone infinitely often. You need to make sure that you can see him within a fixed window. And so it's a kind of attractor property here, when you need to make sure that this label, you can enforce it from everywhere in your BSCC. And in this way, you will know that the entire BSCC satisfies Fp infinite A.
You have looked at the model. Have you looked at the satisfiability problem?
Indeed.
Yeah.
So this is the next step would be to look at, sorry, what did you say?
Satisfiability problem.
Oh, yeah, I thought you said synthesis.
Oh.
Yeah, satisfiability, I don't remember looking at it for this particular fragment.
Yeah, because the first one,
Mhm.
from the boundedness problem, then you don't have the system. Then it is really a true unboundedness problem, true boundedness problem. Because right now it's a pseudo boundedness problem because you get automatically bound.
Yeah.
So
Indeed.
it's a general theory, weak MSO plus boundedness.
Mhm.
They showed that it is desirable, and then finally that entire project came to a very tragic end because they showed that the MSO was used and desirable.
Yeah.
So, yeah, I think it will be interesting to look at fragments which are desirable.
Indeed, it should be related to the thinkings about infinite system in a way, because you have, I guess, the same kind of issues that emerge compared to the finite setting, especially with the distinction with fairness and such, and how it relates to a bound that you could decide.
Any other questions? Okay, then let's thank the speaker again. Yes, so now we don't have a second session, so we meet for lunch or here, right now, here. Okay, it's parallel.
Okay, I think, yeah. Yes. Yeah, very. So, yes, so good morning, everyone. We are soon going to start the RHPL session, which I'll tell you briefly about, which is happening for the first time blended with